Hello everyone, welcome to Neural with Mohit. So we are continuing our RAG series. Our previous video was on text embedding, and today we are going to cover the vector databases. Right. So let us understand what is vector database. First, we'll come here and we will understand that what vector database is, where do we use it, when do we use it, and how does it differ from the traditional RDBMS. Okay. So vector databases are optimized for semantic search. So in our previous video, we have seen that we create text embedding to actually implement the semantic search, right? They use ANN, which is approximate nearest neighbor algorithm, which trade a bit of accuracy for significant faster performance, which means that here the accuracy is compromised with a slightly compromised, but you get results really fast, right? When you compare it with the KNN, which is the K nearest neighbor, which is kind of the keyword search kind of thing you can say, right? So ANN typically operates on and log n. Okay, and now let us understand some differences between the vector DB and the RDBMS. So vector DBs and RDBMS, the differences goes like these RDBMS that you have used traditionally, they actually work on a tradition structural data, right? Which is like the data is very well organized and columns and rows, and you can actually, divide it in that and then keep it, in your vector database, sorry, in your RDBMS, right? And you can actually maintain relationship also between different tables using the RDBMS properties, and you can create the ACID properties and that and all, right? Okay, but when we talk about the real world data is not that structured, because to create a structured data, it requires a lot of cost is involved in that, a lot of effort is involved in that, a lot of time is involved in that, right? So basically, when we come to the more realistic example, in the real life example, the data are mainly in the form of documents. It could be in the form of videos, it could be in the form of images, it could be in the form of audios, right? That these data we cannot store in the traditional RDBMS. So hence comes the need of vector databases. Okay, so last time we have seen that we can do text embedding, we can also do image embedding, we can also do video and audio embeddings. All right, and what we have seen is that once we do the embedding, we actually implement that and then, do the similarity search on that and the other thing. But there are always the cases where once you have already done the embedding, you want to store it somewhere, because then again, you need not have to do the embedding again, right? Embedding also involves cost. When you use some model, you have to provide tokens, and the cost is involved in there, time is involved in there, GPU, CPUs are involved in there, right? So if the text document is there, let's suppose, and that document, if we have already chunked, if we have already converted to embedding, why not store it somewhere and then use it from there itself, right? So that is where the vector DBs comes into picture. Okay. So RDBMS stores structured data, rows and columns, and relies on exact keyword matching. VectorDB stored unstructured data, which is like text, images, audio, videos. We just discussed that, right? As vector embeddings and enable similarity-based search, which means that you will be getting the similar results, right? Not the exact same results. It won't be, like being rigid on the exact same results. Vector DBs are faster for semantic search and are critical in GenAI and RAG, right? So, in the industries that nowadays, you must have heard about the word RAG, and that is the same series that we are also completing. So, in that series, what we are right now learning is vector DBs, and now from here we can see that vector DB is a very important component of RAG, right? Now, since it is a database, so definitely there will be indexing, because to do the search more efficiently, you need different kinds of indexing, right? So number one is the flat indexing, which is like the brute force. It doesn't change to anything. You get the semantic vectors. It just store it as it is, and it creates the embeddings on that itself, right? Another is called locality sensitive hashing. So if I'll give you an example of that, assume that it create different buckets, right? And then based on your text embedding, what it does it finds the appropriate bucket for that and then stores it in that bucket, right? So that is the locality sensitive hashing. Okay. Now inverted file index. Inverted file index is an indexing where what it does is it forms clusters. Okay, and then what it does is whenever a new text embedding comes, it sees that where does it fall, and then it assigns and it tries to assign a particular cluster which is already there. So which group it will fall in, and then that particular thing is done. Okay. Now, in the inverted file indexing only, uh, the, there is another called product quantization, which is like these clusters that you have formed, right? Those clusters are again divided in subclusters, right? So when you do a searching, the search becomes much more efficient. However, this has one drawback, this IVF and IVF PQ. If your result is actually following on the borderline of the cluster, so what it has to do is it has to actually check the neighboring cluster as well for the results, right? Okay. Now, the next one is HNSW, which is also called Hierarchical Navigable Small World. And this is a kind of graph-based indexing where whenever a new embedding comes, it starts from the top level. And then if it is the similar, then it remains on the same level. If it is not similar, then the next level is created and the embedding will come here. And then a link between the top level and this level is created, right? Then again, when the next one comes, not similar to this, not similar to this, a new one is created and a link between the middle one and the last one will be created, right? So like this, what it does is it creates links from top level till the bottom level, like how you can come, and it's a graph kind of structure that you will see. Okay. Now, since we have understood the theory of the vector databases, and since we have understood that why do we need the vector databases, let us now come to the hands-on implementation. You will see the first few steps are same as your text embedding tutorial, right? So what we learned in the previous segment where we were doing the text embedding from the previous video, you will see most of the steps are same, and you will see that I am actually, getting many of the libraries also, they are same. However, there are a few different libraries as well, which are like here ChromaDB is what I have used. So we will discuss those. First, what I'm going to do is I'm going to import the libraries, right? So once these libraries will be imported, then what I will be doing is the same file I am loading, the one that we have used for text embedding, the same file I'm going to use over here as well. You are already aware that it has 142 pages. So all those 142 pages are like we are able to load those. Okay. Now, let before we move further, let us discuss a bit about ChromaDB. So what we are doing over here is we have a lot of options for vector DBs, right? So you have ChromaDB available, you have Fires available, Fires is by Facebook. You have Pinecone available, right? You have Waveit available. So there are a lot of you have Quadrant available. There are a lot of vector DBs available in the market, right? We are using ChromaDB. It's an open source DB. You can use it directly. There is no cost involved in that when you will be using it. Okay, so we are using the persistent client of this ChromaDB. You can also use what we say. The general client of this persistent client, and the difference between persistent client and general client we will come and discuss later. Okay, so for now the vector DB that we are using is the ChromaDB, right? And you have other options also available which are like fires. So just let me write down. Okay, you have Pinecone. Similarly, you have Quadrant. Similarly, you have Waveit. So you can use any of these. Okay. Now let's come to the next part. So we have already, we are able to see the pages. Now, here what we have to do is we have to do the chunking of our data, right? So before we now go here, let us first understand the complete architecture of our application so that we will be able to use it, right? So let us understand the architecture. So this is the architecture of our application. Okay. So what you have seen is I have already loaded the document. Now the documents here is referring to the PDF. Okay. Now after this, what I will be doing is I will be creating chunks of that. In the previous video where we have done the text embedding, you have seen that we have created the page size chunks, right? So each page we actually thought of that it is a chunk, right? You can do a page size chunk, you can do a document size chunk, you can do paragraph size chunk. So there are different chunking mechanisms. We will discuss each and every chunking mechanism, but for the understanding, there are different chunking mechanism that you use, and we actually select the chunking based on what kind of model we are using, because some models might be having a smaller limit, whereas the other models might be having a very big limit, right? So after chunking, what we will be doing is we'll be sending it to the embedding model, and then from there we'll be generating the embeddings. Okay. So in our flow, we are currently here where we have done the ETL. So let me just write the ETL also here so that you know. So we already did the ETL, then we are doing the chunking. Then from embedding model, we are generating the embeddings. Once the embeddings will be generated, last time what we did is we just, used it in memory dictionary, basically array and array of dictionary, right? Here, what we are going to do is we are going to store it in the vector store, right? For us, the vector store is ChromaDB, right? So for us, the vector store name is ChromaDB. Sorry, I have it PT. It's ChromaDB, and this is our vector store. Just let me put it here. Okay, so our vector store will be ChromaDB, and this is the one part of the application. Okay, so let us just say that this is the one part of the application. And this particular part, you have to implement it every time when you get a new document. So, right, so whenever you get a new document, what you need to do is you need to actually implement this particular part where you will be taking the document, creating chunks, then creating the embeddings from the embedding model, and then storing it to the vector store. Okay. Now let us come to the next part of this. Now, the next part of this is where we do the query. Okay, so now the user will come and the user will ask something like we have seen in the previous video as well, where the user came and then they asked that what is the revenue of Uber, right? Similarly, we'll be doing the query, and there also you remember that the query we converted to embedding using the embedding model. Now, here one thing you have to notice is I have like actually use the same embedding model block here, right? I have not created a different block for this. Now, the reason for that is whatever embedding model you are using to create the or to generate the embeddings for storing in the vector store, you have to use the same embedding model with the same configuration to generate the embedding for your queries. Otherwise, your query search will fail. Right. So after this, what we will be doing is we'll be hitting the search, right? But first, what we are doing is we are checking in the local cache if the value is existing there or not, right? So if the value is existing there, then from there, what we will do is we will send the results right away, right? But if it is not a cache hit and it's a cache miss, so in that case, what we will do is we will actually go to the store and do a search over there, get the results, and then store those results in the cache first. And then from there, we will be sending back the response, right? So this is the whole architecture of our application. Now let us use it over here. So we have already seen ETL we did. Now comes the chunking part. As I said that there are different chunking mechanisms. So you can see all the chunking mechanisms over here. We have fixed size chunking where you define that I want the chunks to be of this particular size. You have sentence based chunking where you create chunks based on, let's suppose, on full stop. So whenever a full stop is there, that is one sentence for you, and you will be creating the chunks from there, right? Paragraph based, there is page based. Page based is what we actually are using here. So there is page based, then there is token based, there could be new line based, right? So sorry, here I have written this. It is not actually this, this is end of sentence, right? And then there could be one new line based chunking, right? And here we will be writing backslash n. Okay. Paragraph generally it has multiple this, so we are writing like this, right? Page based there, token based there, sliding window. Sliding window something like you create a chunk, and then the next chunk will contain some part of the previous one also, right? So that it doesn't lose the context. So it will be carrying some context from here, and then the next chunk is created, right? So that is how the sliding window works. And like this, all the chunking mechanisms are here. You can actually read about these. You can take these one-liners are already written for you, and which is enough for you to understand, right? Okay, now let us come to this. Here, what I'm doing is, if you can see, I'm trying to do the split based on. So first, I'm actually taking the pages. I'm doing the split on pages, right? So, and in each page, what I'm checking is I'm checking if there is a backslash n there. In that case, I'm splitting it and I'm writing it in the same like I'm creating the chunks based on the new line in this, right? So this is also one kind of embedding. However, I'm not going to use this one. I already said that I'm going to use a page-based chunking here, right? So this is just for an example, just to show you how the new line-based chunking works, right? Okay, so what we are going to do is we are going to implement what we say. Uh, our page-based chunking on this. So we have a text content array. Okay, and then I'm taking the document name. This logic is exactly same as we have we've seen in the previous video itself. Okay, now let's come here. This is also exactly same. We are extracting the text. There is just one thing that you will notice here, which is like I'm checking if the value, if the number of words in my document are less than 10, then I'm not considering that record, right? So I'm ignoring that one. So continue, what it will do is, if this satisfies, then it will again come to this loop and start for the next iteration, right? Okay. Now, another logic that you need to check is, I'm checking if the length of my text is more than 5,000, right? So in that case, what I'm doing is I'm actually checking that do I have let's suppose splits or not. So I'm splitting based on backslash n, and then what I'm doing is I'm actually taking the item I'm splitting it from 0 to the mid index and then from the mid index plus 1, right? So this is what I'm doing over here. And if it is not there, then I'm loading the complete document, right? So basically what I'm just doing is if my text is too large, I'm just dividing that into two, items, and then I'm putting each item in the same page, right? However, when I'm putting that, I'm also mentioning that what is my split number. So here the split number is 0, and here you will see the split number is 1, right? And if I'm not splitting, then it is 0 itself, correct? Okay. And what I will be like doing with this, will come and see that later, right? Okay, so now here, let me first run this. So this will take some time. You can see that page one is having very less count. It has only 5 items, right? And then you can see page 139 has only 2 count, page 140. So these I'm less ignoring, I'm not using them. Right, and here you see the first item is the page number 2. Like in the previous video, if you notice, our first item was page number 1. Here we have page number 2 because of this logic that I've added. Right. Okay, cool. So let's move to the next one. And let us see, because I've increased the counts over here. So let us also check that what is the count. So earlier you notice in the previous video it was 142, but this time it is 205 because many pages are having more than 5,000. So in that case, we must be splitting them in two, and hence this particular number, right? So you have these many documents this time available that you are going to load to your vector store. Okay. Okay, now after this, the same thing, we are creating the data frame. The data frame will be of these columns, right? And this time, from these columns, what I'm just doing is I'm extracting the metadata and the content, right? Metadata, what it is? It is document plus page plus split plus type, right? So this is my metadata, okay? And then after this, what I'm doing is I'm creating the embedding for this. So it will take some time, depending on how big your corpus is. It will take the time. And right now the embedding is created. Okay, so I have this embedding now, and now you see this folder. This is currently empty. So if you'll notice over here, I'm saying that in my store, in this particular folder, I want to store this collection, right? And here I'm using the persistent client. And if you notice, I kept this commented. So you can like comment this and use this one as well. This will be the in-memory store. It will not store it to a file. However, when you create a persistent client of ChromaDB, it also stores it to your hard disk, right? Wherever the local storage, basically the location, the path that you will give, it will store it over there. So next time when you are, like even if you kill your kernel and start again, you don't have to do this embedding step all together again, right? So you can actually bring this in the beginning only. You can check if it is already there, then use it directly. Okay, so I'll just run this. Okay, and now if you notice, you can see that a new DB is created, right? However, this DB right now does not have anything. So you see only the DB is being created and nothing else on top of this, right? Okay, now here what I'm doing is I'm creating the IDs, and the IDs how I'm creating. I am actually taking the metadata, which is this value, basically, right? And I'm creating the document underscore page, the page number, and then underscore S, which is the split number. Okay, so I will be creating these, and if you like, as you can see, for each, like it will be having page two split zero, page three split zero, page four split zero, like this. It has created the indexing, and the indexing for each document will be different, right? Okay, so now we have all the relevant detail. We have the content, we have the metadata, and we also have the IDs. So what we are going to do now is we are going to create the collection now. Okay, now collection, if you see, it is this thing that we have already created, and the name of the collection will be Uber revenue that we are going to create. Okay. Now, if I run this thing, so it will take some time because it is going to create the complete collection for you, and then it will be storing it uh, and creating the indexing and everything for this. So you can see that earlier when the data was not there, there was only this. Now when the data is also there, you can see these many new files are created, right? Okay. So till here we are like we are done, right? And if you notice, what we have done is like we first got the documents, we divided the document to chunks. After dividing into chunks, we created the embedding. After creating the embedding, we stored it in the vector DB. Okay, so now we are done with the boilerplate thing, right? Now the next thing should be where user can come and do the query, right? And if you remember our architecture, uh, here you can see that what we are doing over here is after storing in the DB, whenever the query will come, first, we will be creating the embedding for the query, and then we will be checking our local cache, right? If it is there or not there. If it is there, then we will be returning from here itself. If it is not there, in that case only we will be hitting the vector DB, getting the result, first storing it in the cache, and then returning it back to you, right? So let us see how we can do that. So for this, you will see this particular function, right? And what this function is doing is it is first whatever query is coming to you, it is creating the embedding of that query, right? That is the first step of the query, create the embedding. Now the embedding is created. After this, we are checking, do we have any cache? Like when the cache is zero, then there is no point in checking as well, right? So if there is no cache, then forget it. But if there is, like if you have the cache, then what you will be doing is from the cache embedding, you will be like creating the array of that, and you will be doing a similarity search in your cached item and your query, right? And in the cached item, what we are caching also, we will check. Okay, so I'll come to that. But right now, for your understanding, what it is doing is it is doing a similarity search between your cached item and the user query, current user query. Okay, and it will get the best match index. And then in that, we are checking that first of all, there should be some value, right? And second is the value should be more than zero point 0.8. If that is less than zero point 0.8, if the similarity score is less than zero point 0.8, then that is not that similar for me to actually use the caching, is what my logic is, right? You can play with this value, you can change it to 0 0.6, 0 0.7, 0 0.85, whatever you want. Okay. Okay, so if I'm getting the value, then what I'm doing is I'm returning the value from here itself, right? I am actually not making any call to my vector DB, and that is the same thing we discussed there also. If it is a cache hit, in that case, we'll be coming here and we'll be returning from here itself. Okay. Okay. Now let us come to this particular part. And like, let's suppose this condition is not satisfied. In that case, what will happen is we will come here. We will do a query search on our vector DB. And I'm saying that I want the number of results to be three, right? And after doing the query search, yeah. After doing the query search, we will be getting some results, and those results is what I am appending to my caching first, right? So I'm saying this is my query, and these are my results. This is my caching array, and this is the cache embed. And what it is doing is this embedding, it is storing in the cache embed, right? Now, if you notice, this cache embed is only keeping the query, not the results, right? Because what I need to check is I need to check the similarity between user queries. If the query similarity is more than 80, like zero point 0.8 for me, right? So in that case, I will be like, okay, it's a very similar query. I can return the results from my cache itself, right? Okay, great. So we'll execute this function. Okay, and now it is time to call this. Now, for the first time, there won't be any results, right? So, since there are no results, so when I will make and when I will hit this particular uh, line of code, so what it will do is it will go here, it will check this condition will not satisfy. So, it will directly come here, it will get the result, store it in cache, and return the results, right? So, let us do that. Okay, great. So, see, I actually made a query saying that. What is the revenue of Uber. And what you can see over here is I am actually getting the response from my vector DB. And it is saying that, you can check this page 79, page 98, and page 58. And here there will be three documents basically, right? Because I have said that I want the number of results to be three. So the three documents here. These are the three indexing of those. And this is the associated metadata of that, right? And along with this, I am also getting the distance, right? Now, here you have to understand one thing, a difference between vector DB distances and cosine similarities. Cosine similarity, higher is better. Vector DB distances, lower is better. So if the distance is near to zero, that means that the confidence level is very high there. Those values, the value that you are getting is, almost same, right? Here we are seeing that the distance is 0.58, 0.65, and 0.70. This is the same order in which you will be getting these, which means the document first document is having the highest relevance, then this, and then this. Okay, so you got this particular thing right, and you also saw that first time that there was no caching, and we actually did this. Now, in our cache, what we'll be having is let me just add one row. Let me delete this one. I don't need this. Okay. So here what I'm just going to show you is that what do I have in my cache? So if you will see in my cache, I'm having this query that what is the revenue of Uber and then the result of that, right? And similarly, if I will say that what do I have in my cache embed, then you can see that I have this particular embedding of my query, right? And if I'll just do a length of this, so, oh, sorry, it was like this, yeah. So if I do a length of this, okay, it's coming as 0. Anyways, so it is like, oh, okay, sorry. So inside an array, there is another array. So it's like when I said 0, this is the first one, right? Because it's an array of array. Then the second 0 is actually giving me this result itself, which is again just one item for it, right? Inside that, again, if I'll see, so I will be getting the dimension of this, right? But we know the dimension of this. It will be 384 because we have used the same model, right? Okay, so now we have till here. Till here, everything is sorted and we know everything. Now let us do another query. Okay, and this time I'm going to do a query. What is the profit of Uber? Okay, now my previous query was what is the revenue of Uber? This time it is what is the profit of Uber? And to me, if you'll ask, I see that they are quite similar to each other, right? So let us see what will I get this time in the results, and let me delete this so that we'll be having less extra space will be taken. Okay. Great. So now, if you will see this time, it is saying that returning from query, right? Which is this one, returning from query, which means this time we actually got the result from the cache. And if you see the similarity score is 0.91, right? Which means that what is the revenue of Uber and what is the profit of Uber are very similar queries. So I need not have to make the DB call again because last time I've already did this, right? So what I'm doing is I'm just extracting the same results and using it over here, right? Now let us make another query, which is like what is the loss of Uber? Now this time when I did, so it did the query matching and it must have found that okay, the results are not that great. And in this particular case, what it is doing is it actually went to the store and then it started extracting the results. And if you'll see, I am getting the results over here, which are like page 84, page 79, and page 98, right? And then these are the distances in that 0.77, 0.81, 0.82. Okay, let us do something more, which is like I'm hitting just right now. I'm just trying out different queries. How much degrade for Uber? So here also it must have gone through these queries and it must have not found any similar queries in those. So what it must have done key, okay, let me get this result and go to the store and get this particular result for you. And here also if you'll see the distances are like this, right? Okay, so we have seen one thing in our architecture, which is like only those queries we are storing where we go and do the vector DB search. If you actually query something for which the vector DB search is not done, that query we do not store. Okay, cool. So let us do few more queries. This time I'm querying how much negative margin for Uber. Okay, it went and it did the vector DB search and it must have got the results, and the results are like these 84, 79, 78. These are the pages it has found. Then what is the margin for Uber? Now the margin and profit are quite similar to me, right? So it is saying that how much negative margin for Uber. Oh, nice. So we actually did the last query as how much negative margin, and in this, it must have got all the margin results also. So what it did is it actually brought the results from the previous one itself, saying that it has got a confidence of 0.89. Okay, and how much money Uber made. Now this is again similar to what we say the revenue wala part, right? So here you will see returning from query, what is the revenue of Uber? 80% like 0.80, and then these are the results, right? So now you have seen that how we implemented this complete, just iterating it one last time. Create the documents, form the chunks from there, send it to model, embedding model, create the embeddings and store in vector DB, right? Next time when you do the query, use the same embedding model, create the embeddings, search in your local storage or local cache. If it is there, send the results from there. If it is not there, then in that case, search the vector DB, store the results in your local cache, and then send the response, right? So this is how you can actually implement this complete semantic search with vector DB. And we have completed two very, the strong pillars of RAG, which is number one is embedding and number two is vector DBs, right? Now, the next time when we will be meeting, we will be implementing the text-based RAG system, where we will be using a large language model as well, basically a generic chat model as well. So what we'll be doing is the results that we have got over here, right? These results, if if I tell you these are very bookish result, right? Because I have to read this complete and then understand. So what I want is I want to give it to my LLM itself and say generate a summary from there. So that is what we will be doing when we'll be implementing RAG, right? So we have already implemented half of that. The half of that means we are already done with, storing it to DB and then getting the responses. Now these responses only is what we need to feed to the LLM and generate, the results from there. So we will see that in the next video. Till then, let's practice these. And what I would like you to do is I would like you to from the PDF also extract the images and also extract the text and the tables, and then try and create an embedding for those, store it in DB, and do a DB search, means basically similarity search on that, right? Okay, great. So with this, we come to the end of this particular video. I would like you to like the video on the YouTube if you liked it. Share it with your friends so that they can also learn about this RAG, and also subscribe to the channel. Thank you.